Hello guys, and welcome to the third lecture of the CONVERGE channel. I am Mansur Amini. In this session we are going to simulate pressure swing distillation by HYSYS. So let me say you something first and jump into the HYSYS simulations. We have two ways to actually separate azeotropic mixture and composition. The first one is that you just insert one entrainer and extract or changing our azeotropic composition and separate our component. And the most economical way, the second way, is just to use, for example, two column and put them after each other in different pressure to just shift our composition azeotropic component or mole fraction. So let me explain this on this diagram because it's more effective to just understand the way we use pressure swing distillation. So the blue curve which you can watch in here, the blue curve is in the pressure of 0.5 atm, which its composition mole fraction azeotropic composition is equal to 0.37, and after changing the pressure, our green curve, our composition change significantly and reach to these numbers. So let me explain you how to simulate pressure swing distillation using HYSYS. In the PFD we have the feed flow rate and composition as well, toluene and ethanol at temperature of 30 degrees C. The first column is pressure is equal to 0.5 atm, and we increase the pressure to 11 atm to just separate our composition. So let's jump into the simulation area and insert ethanol and toluene with their mole fraction. Just start the session by opening up Aspen HYSYS, insert the component just right here, so go to fluid packages and add an RTL fluid package. Actually select an RTL fluid package because we have ethanol, and NRTL fluid package is the most proper fluid package for our simulation. So insert the feed stream. Let me change its name to feed. Our feed is in 30 degrees C and our pressure is equal to 0.5 atm. 0.5 atm. Just make sure that you choose the unit of atm. So the mass flow is 3,500 kg per hour, which is given right here, and insert toluene and ethanol one fraction right here, 0.72 for the ethanol, and toluene is equal to 0.28. So after inserting this criteria and condition which given here, our feed completely defined. So let me insert the distillation column. we have the feed. Just select total compressor and name this stream as well. So let me name it D1, bottom 1, and duty of the condenser for the pressure column number 1, and Q of the reboiler for the column number 1. A number of trays are given right here, 34, which our feed stream goes to the tray number 6. Insert this criteria as well, 34, for the total number of our distillation column, and our feed is going to tray number 6. Go to the next page. This is optional, you can skip this. Condenser pressure are given into the PFD, which is equal to 0.5, and reboiler pressure is the same. The pressure is the same as condenser because our distillation column work at the actually constant pressure, and we do not change the pressure in the distillation column, especially for the azeotropic composition. Go to the next page and insert above 60 degrees C for the temperature. So this is optional, you can just skip this page without inserting any number. So ratio, reflux ratio, I do not have any information about that. I just insert 2. I will change it after running the simulation. So go to the monitor, and degree of freedom is equal to 0, which means we can run our distillation column. So let me first actually define this stream which recycle and came back to the first column just right here, and again run the simulation. So let me insert this stream as well. Name this as rec with temperature of 155. Pressure is equal to 11, and we after running our simulation, we insert one valve just right here to decrease our pressure to the pressure of the first column for just running our criteria as well, and properly running of the first column. So the flow rate is equal to 3148 kg per hour. T148 kg per hour, and go to the composition, insert the composition just right here, which is given right here, 0.85, and for ethanol 0.85 for ethanol and 0.15 for the toluene. So after simulating this feed stream, we do not insert the pressure, just insert that. and after determining criteria of the recycle, go to the column and insert rec as our recycle to the tray number 60. Go to monitor. Degree of freedom is equal to 0, as I said, which means that our column can run, but because we activated these two options, and we have to insert the distillate rate. So let me explain how to determine this distillate rate for running your simulation. Go to the PFD. We have 3,500 kg per hour for the feed and about 3,000 kg for recycle. So our distillation flow rate should be actually maybe just be half of sum of these two streams, which is equal to 3,000 kg per hour. So insert 3,000. Let me just click on run and change the molar to the mass flow and insert 3,000 kg per hour. This is our first estimate, which maybe it's not going to work. Just change this number to run our simulation. For example, I insert 2,000 for the distillation. So let me say you something first. Go to the parameter and go to parameter solver and make sure that you activate this option, because our composition is azeotropic, and again run the simulation to just make sure to just running and converging our distillation column. Just make sure that you activated this azeotropic right here. So after simulating the first column, we need to increase the pressure to the 11 atm, and in actually its distillation rate is the entrance or feed of the second column. So we need a pump. Insert the pump just right here. Press Ctrl and drag this stream to the pump. We need an energy stream for the pump. Let me change this to the outlet pump. So our pressure is going to reach to 11 atm. Just insert the pressure into the outlet stream of the pump, and our simulation is completely run. So again, go to the distillation column. We have a distillation column with 21 tray that our feed is going to tray number 60. Insert the second column, go to separator and distillation column. Just insert this to distillation column. You can easily insert or define your stream, because it's more easy. Just press Ctrl and drag your mouse to just define. So go to total and just select the total condenser for your distillation column, and this is distillation number 2. So we have 21 tray, which our feed is going to tray number 16, which is given just right here. So we insert all these options. This is optional. Condenser pressure is equal to 11 atm, and again 11 atm. As I said, we have the constant pressure in the distillation column for just separating our azeotropic mixture, and insert 155 degrees C as the first estimate of the temperature of the condenser for the second column. 155 in degrees C. This is optional. You can just skip this, but for a better converging your distillation column, I actually recommend you to just insert this temperature as well. So go to reflux ratio, I insert 2, click on done. So we have all the information just right here. Go to the monitor again. We have degree of freedom, which is equal to 0, and we have activated these two, and we should insert distillate rate for our running converging our distillation column. So let me again guess how much distillate rate need. We have our feed flow is just 2000 kg per hour, which means we can, for example, enter 1000 for the flow rate, actually this distillation rate. Change it to the mass and insert 1000 kg per hour as our first estimate. I don't know, just half of the our feed stream can be for the distillation rate for your first estimate. So go to the composition of just right here. We need to change, just we need this mole fraction, which is not equal. We have this composition right here. Just let me insert the table and add variable. Go to the master component, mole fraction. So let me master component mole fraction, which is toluene, and select toluene as your master component and click on done. So let me remove this variable. So we have composition of our toluene just right here, which we are going to reach this number to about 1 So let me change the our spec for just make sure that this number reach to the criteria which we are looking for. This insert tree, for example, as you can watch, as you increase the reflux ratio, our distillation column work better. I insert 1200, for example. It is not going to work. Just insert 1000 again. So make sure that you actually select this as well. Just run the distillation column again. Just click on reset and run it again. So let me change this after completing our simulation. So we need to decrease our pressure, which is equal to 11 atm to the 0.5 atm. So we need a valve. Go to the all and insert a valve to the simulation area, and let's simulate a valve which its pressure is going to reach to 0.5 atm. Just go to the modify and flip it horizontally for just better outstanding. So our pressure reached to the pressure of the first column. We can insert this stream to the first column easily. So we need a recycle to bring back this stream to the first column. Bring recycle to the simulation area again. Just simulate it. So break this connection and delete this connection and insert this to the first column. Go to the first column again, go to design, and this is our recycle which goes to the tray number 16, which is given right here. So let me change it to the tray number 60 and again click on run and our simulation works. So after inserting recycle, our composition of the toluene in the bottom of the second column make better and our distillation column work better, but this is not the criteria which we are looking for. So let me add some new spec to just reach this number to the object or aim that we have in the PFD. So go to the design again, to a spec and add column component fraction. Add this spec which is in the reboiler section, small fraction, and we want to reach to this criteria. our component is toluene, and just select toluene right here. So after inserting this criteria to the go to the monitor again and just deactivate the first spec and active the new spec that you insert. So let me change it to the 82. Stop the simulation and again deactivate this one, and let me try this with this one. So run the simulation. So after changing your spec, your distillation column work. So let me change it again to 90, for example, 2. So it converged. So let me change it to the 99. So we reached to the criteria that we were looking for, and which is given here, 99% of mole fraction for the toluene component, and we need to just modify this ethanol, which is the bottom of our first column, and reach this composition to 99%. So go to the simulation again, and let me check out the composition, which is 0.81. So go to the distillation column. We are going to add the same as aspect that we inserted to the second column component fraction at this spec as well, this reboiler stage, and mole fraction, liquid, and 0.99 for the ethanol. So after inserting this, go to the spec summary, just deactive, for example, reflux ratio and active component fraction. So again, let me stop the simulation and change this spec and try this with the reflux ratio. So our simulation is completely done. You can watch your criteria right here. Go to show table, and let me delete this one. Go to the show table and remove this variable, which we do not need. This one, add variable, and insert master component mole fraction. So let me try it again. Mole fraction, which is ethanol. Just insert this one. So let me skip this one. So this is a master component mole fraction in the first column, which is equal to 99%, and the second column is for the toluene, which is 99%. So our simulation is done. If you have any question about the simulation or understanding of this PFD, just let me know in your comment, and I will answer your question in the comment. And if you found this video helpful, just share it with your friends, and please like and subscribe my channel. Thank you guys, have a good time, bye bye.